Inside a black hole lies one of the universe's greatest mysteries. Space bends, time stretches, and the laws we rely on begin to break down in strange and unpredictable ways. A black hole forms when a massive star explodes in a supernova and its core collapses, creating a region of gravity so intense that even light cannot escape its pull. In cosmic maps, a black hole appears as a dark, swirling vortex. Its powerful gravity can pull in stars, gas clouds, and any matter that wanders too close. Near a black hole, beams of light bend dramatically. This extreme curvature shows how powerful gravity becomes, capable of warping the very path of photons themselves. As an object approaches a black hole, gravity strengthens rapidly, stretching and distorting its shape. This explains why matter seems to stretch as if it's being swallowed. The event horizon is a point of no return. Once crossed, nothing, including light, can escape the black hole's immense gravitational pull ever again. A spacecraft nearing the event horizon would experience intense time dilation. According to Einstein's theory, time slows dramatically under such overwhelming gravitational forces. Light emitted near the event horizon tries to escape, but is dragged back in. This demonstrates the absolute power of gravity at the boundary of a black hole. From the outside, an object falling toward a black hole seems to slow down, fade, and freeze in place. It never appears to fully cross the horizon. Once the event horizon is crossed, the falling observer notices nothing unusual. Yet from this point onward, no signal can return to the outside universe. Spaghettification occurs when tidal forces stretch the body severely. The side closer to the black hole is pulled much harder, creating an extreme stretching effect. Matter falling inward is pulled into thin, elongated strands. This tidal tearing destroys the object's original structure at both the molecular and physical level. Even molecules stretch as they near the black hole's center. Gravity becomes strong enough to break apart the smallest bonds that hold matter together. Material layers peel apart as they move deeper inside. Enormous tidal forces tear every structure into thinner and thinner sheets of matter. Before disappearing completely, the object is stretched like a long spaghetti strand. This is its final moment before being absorbed entirely by the black hole. At the center lies the singularity, where density becomes infinite. Space and time collapse, and all known physical laws lose their meaning entirely. All streams of falling matter converge into a single point. The compression here is so extreme that no current scientific model can fully describe it. Space-time twists violently near the singularity. The grid that represents the structure of the universe becomes distorted, unstable, and almost unrecognizable. Even familiar physics equations and concepts break down near the singularity. It is a region where our understanding of nature simply stops working. At the core, space and time lose their coherent form. Everything bends, twists, and collapses into a state that defies logic and physical interpretation. Some theories propose that a small universe could exist inside a black hole. A miniature Big Bang might begin from the singularity, forming an entirely new cosmos. Einstein's relativity and quantum mechanics clash when describing black holes. These two powerful theories still cannot be unified to fully explain such extreme environments. The firewall theory suggests a blazing layer of intense energy around the event horizon. If true, anything falling in would be instantly destroyed by its heat. The soft hair idea proposes that black holes store unusual forms of information. Tiny photons around the event horizon might carry traces of what fell inside. Quantum information falling into a black hole becomes warped and altered. Yet according to quantum theory, that information cannot disappear completely, creating a major paradox. Some models propose that black holes may release information through radiation. This idea attempts to resolve the famous information loss paradox that challenges physics. Information entering a black hole seems both trapped and recoverable, creating a contradiction. This dual behavior remains one of the biggest puzzles in modern science. Another theory suggests black holes encode all information on their surface. This holographic idea explains how data might survive even as matter is swallowed. If someone fell into a supermassive black hole, they might pass the event horizon without noticing. But deeper inside, tidal forces would eventually crush their body. Small black holes tear objects apart instantly, while supermassive ones apply gentler forces at their edges. The falling experience depends on the black hole's size. Inside a black hole, radio waves and light signals vanish completely. Nothing can be transmitted outward, making this region totally isolated from the universe. Black holes remain one of the universe's greatest mysteries. Despite decades of research, many questions about their internal structure remain unanswered. The physical laws we rely on fail inside a black hole. This challenge pushes scientists to search for a new unified theory that explains gravity and quantum behavior together. The universe is vast and full of wonders, with black holes being just one extraordinary feature. Observing them from afar evokes both curiosity and profound awe.